Okay, we're going to go on to 6.2, which is vector addition, which is pretty straightforward. And in this section, you'll need skills of the cos law and the sine law, because figuring out the line distance is easy enough, but figuring out the angles is the tougher part. And you'll look at situations like this when you're adding them. You just add head to tail and draw the conclusive line, and you'll be able to figure out angles if you're given certain angles. And there's certain laws of triangles and total degrees within a triangle, within a square, that you'll have to be aware of. But it's pretty straightforward. If you're fairly good with cosine law and sine law and Pythagoras' theorem, you'll be pretty good at adding them together. And that's pretty much what they summarize right here. This is the cosine law and how you come up with the conclusion of a distance of a line, and that you can essentially figure out angles if you're given enough information. They're always going to give you enough information. And the difference one where you subtract two vectors, you just make one vector go the opposite direction but have the same magnitude. We'll go over that as well. And then they go through the box and the tough thing of finding the diagonal from O all the way to F, which is a three-dimensional line, and the secret is just finding it based on a two-dimensional line and then again on the third dimension. We'll get to that as well. And a lot of it will be speeds, distances. This one's about a plane heading south with a easterly or westerly wind and where its new course is. And a lot of it will also be like which direction should you point if you want to end up at a certain spot, which is kind of what ships and planes do based on the winds. Always just jump to your summary, and if you understand the summary, jump ahead to the questions, because the questions are where you will gain your skill, not in reading. Always just, if you want to do the shortest way to get good at math, jump straight to the questions, and the questions you don't understand, YouTube a video or go back in the textbook. So below, we're going to add these two. We're going to subtract one from the other. We're going to subtract the other one from the other. We're going to make both of them negative and add them together, and it's just to show you how to do it. So let's start by adding them together. So I'm going to take my black line and assume it's that. And I'm going to take this line and assume it's that. Okay. And since they both point this way and this way, this red line here would be adding them together. Pretty clear, pretty obvious. And so they would be talking about figuring out that red line. And if they give you the distance here and the distance here and the angle here, you can use the coastline to figure out both that distance and all the other angles. Okay, and then once you figure out this distance, you can use the sine law to figure out all the other angles. So what about this one? Well, essentially this one's a negative y, so you would put it the other direction, like that. Okay, and you would put the arrow at the other end. So now we can still add them tail to tail. I just keep this one normal. Go like that. And you add them head to tail, head to tail. So this one, they're not looking for the same red line, they're looking for this line. And you can see it's quite different from the red line over here, this green line. So this is the line they're looking for, this green line. And here, they're reversing it. They're taking the normal, keeping the y the same, but they're reversing the x. And that's to keep in mind of how to do that. When you see this or this, it's the same as x plus minus y. And this one here is the same as y plus minus x, which just means you're making the one vector go the other direction, the opposite direction. That's pretty easy. So again, looking at that, and we're pointing in the opposite direction. that. This one, the opposite direction is this one. And this one kept the same direction this way. So that means the resulting line is this red line. So this one's A. This one's A. This one is, the green line is B. And this red line here is C. I should have kept them all red lines. And here they're just essentially making both the vectors the opposite direction and connecting them head to tail. So we're working on that one for X. So it's now going this way. And we're working on this one for Y. But it's now going this way. And this time I'll make the green line connect them. The resulting vector is that. And you put an arrow like this. And you know you put an arrow like that because you started here and you're ending over there. And again, if they give you a side, and an angle here, you can use the cosine law to figure out the distance. They just want you to get comfortable adding and subtracting. So given this, we'll copy both these. Okay, so given this triangle on the left, draw the appropriate arrows on each side of the triangle to give a single vector of when you add BC. So BC would be this direction with CA, and CA would be this direction, which means the resulting vector is simply B to A because it was this direction and this direction. Whenever they put the BC, that's the direction you're going. You're going from B to C. And so that means your resulting line is this one here, which is simply BA. So you would draw it like that, and you would put an arrow like that, because you started here and ended there. AB is this way, plus BC is this way, plus CA is that way. So we actually, the resulting area is nothing. There is no resulting area. You just ended up back at point A. So the answer would just be point A. There's no line, because we didn't move. We essentially didn't move from where we started. AB minus AC is the same as AB plus minus AC. And what's the opposite of AC? It's CA. So you can just say AB plus CA. So AB plus CA, if I do it in red lines now, AB. Now CA is over here, so I'd have to do it like this, and then put it like that, and the resulting line is this black line here. So that's the vector I end up with. So that means if I started here, I'd end up over here, outside of the triangle. Okay. And minus BC is the same as the opposite of BC, which is the same as CB. So the direction just changes. Plus BA. CB is this one. BA is that one. So the resulting line is this red line. So essentially the result is CA in that direction. Given the following vectors A, B, C, construct vectors equivalent to each of the following. A plus B plus C. So you're just going to add them. So there's A. A little bit off. There we go. Close enough. There's B. It's going to be a little bit off, but I'm just showing you the connection. And here's C. Now notice C is going the other way, so I got to go this way. Then if I connect the lines, it's this green line here. So my answer would look a lot like that. Of course, if I leave it here, I can figure out various triangles and angles and lengths. You might say, well, how do you figure out a length from that? First, you would construct this triangle, right? And you'd figure out this angle, and this angle. And once you have this angle, it's possible, depending on if what extra information they've given you to figure out this angle in here. But once you figure out this length here, and you connect this triangle like that, and you get this angle and this angle, you can figure out this length. And then ultimately, if you look at this triangle here, it's hard to see, but you'd be looking at, and I'll do it in black, that triangle, and that triangle. And so to figure out this side of it, all you would need is that side, and this angle here in this corner. And then you'll be able to figure out everything you want about the final vector. So you're able to chop up triangles and figure things out as you go. And you have to remember a couple rules that are helpful. Here's a couple rules that are helpful. This angle will equal this angle, and this angle will equal this angle. That's just a rule. Here's another rule. If you have two lines that are parallel, like that, this angle will equal this angle. And if I draw a dotted line here, this angle will equal this angle. They will both also add up to 180. So those are a couple rules. And that always helps. And here's another rule. If both those lines are parallel, and I draw a line straight down, this angle here and this angle here should add up to 180. And if they're the same length, this will also be parallel, but it all depends. So there's a couple extra. And also, if you draw a dotted line beyond, this angle should match that angle, and this angle here should match that angle there. So there's a couple theorems like that that help. And then finally there's the S1. This one's the S1, and this one's the Z1, and they have the same kind of principles. This will match that, that will match that. And also for triangles, you know that they all will add up to 180. And for parallelograms, if this is the angle and this is the angle, since they share this side, these two triangles will be congruent, assuming this is parallel with this. And that's because this angle will match this angle, and this angle will match this angle. And so from angle, side, angle, they are congruent. So you also want to know what congruence, how to figure out congruence. And then finally, things with four walls, no matter what the angle, they will add up to 360. And I believe as you add an extra line, so in this last one, if I add that, that, and that, so now that it's 5 walls, it's a different formula. I think it's another, I'd have to look it up. I think it's an extra 60 degrees, but we'd have to look it up. Essentially, the more side you add, you're adding a certain percentage each time. There's a simple rule for it, and I forget what it is. Back to this. So we're adding A, we're adding B, and we're essentially adding the reverse of C. So let's take the reverse of C. The reverse of C is this way. Like that. And just add a tail so that you can remember the reverse of C. But we're adding A to it. So let's also start with A, like that. We're adding B. So we're starting like that. And don't forget that both of them are like this. And then finally we're adding this last C that I just drew here. I could just move it down, but I'm just going to redraw it. There we go. Like that. Which means the line we're looking for is this green line that goes from here to here. Now notice that forms a four-sided object, which means they're going to add up to 360. And so if I have enough angle information about these 3 different angles, I can figure out this fourth angle, and I can also divide it up into multiple triangles to figure out ultimately the opposite side. Okay, what about the next one? The next one is, well, we're just doing 3 now, right? Okay. The next one is simply, this one stays positive, but these two go in the opposite direction. So that means I take my original green, and I should keep my originals just in black. So it's going in this direction, but I'm going to reverse my direction of my other ones, which I'll make in green, and still add it head to tail once I reverse them. The nice thing about this paint is I can, that's not quite, but whatever, so I can keep my lines almost exactly as they just draw them. And then finally, this is the line I'm looking for, from this tail to that head with this arrow. So the result would be the red line. And of course you can figure out various angles. Now this one, you're keeping the A positive, you're subtracting the B, so the B is going in the opposite direction, and you're adding the C, so everything's normal except for the B. So you take A. Now interestingly enough, I want to show you something. If I take A and then I subtract B, so it's going the other way, right? And then I add C, which is what this thing is asking me to do. So there's C. Okay. I end up with this red line, correct? But it doesn't matter what order I add them in. I can start with the opposite of B. Right. I'll make that in green, so keep it consistent, like this. I can add the, I can now add the, let's just add the C instead. Like that. Just remember you got to add them head to tail, because B is reversed, it's a little bit like that. And then finally I can add A. And then when I connect them, like this, I end up with the same line. It's the same line. I also end up with the same basic shape. Well, actually, no, I don't end up with the same basic shape. But the commonalities are interesting, because this one just ended up over here originally, and this one ended up over here originally, and the black one was just here originally. But you can see some commonalities. The red line here is the exact same angle and length as this red line here. It doesn't matter how I added them, so long as I added them according to the pluses and minuses. Okay. Now I think what they're aiming for here is that you should construct the things in brackets separately, but they're showing the distributive property, which is what I just showed. They're showing that it doesn't matter how you add them together, it will result in the same thing, but they're kind of asking you to do them separately. So let's start with this B instead. Let's add A and B together. Okay. And we're going to draw the result of that. The result of that is this green line right here. And now we're going to take the green line as a separate entity, and we're going to add the black line, the C line. And do it like that. There we go. And we're going to try to remember that this green line over here was like that, and this black line was like that. And the resulting line is this red line, and they're trying to show you the exact same thing I just showed you, that no matter how you add these things up together, you will end up with the same result. So now they're asking you to add B and C instead. So B and C. If I add it, I've got that. And then I add this, I got that. So the resulting green line, and I just got to keep track of the heads and the tails, is that. So that's the resulting green line. Now if I add A to it, which is this, and I try to remember it's like that. Let's see, I've got to make sure. See, I've got the wrong one. So there's B and there's C. I've added together and I get that. And I've got to add it to the right side. I'm adding it like that. And then I draw the red line. And it's very similar to what I showed you before, is that the red line, even though I've drawn it poorly here, is the exact same as result. Even though I added them in different order, that red line shares the same commonality with the original one. Different shape, but same result. Okay, so this just is easier when you visualize it, number 5. And let's just imagine 3 points, P, Q, R, and S. And we'll just join them. So it's saying P to Q, so like that, minus R to Q, which is the same as QR, so Q to R, plus R to S. Well, it's clear that when I join these points, I have this point, P to the S. So when I add all that up, it's P to the S, because that's the beginning, that's the end, not SP. That's not right. That's the other direction. Okay, the same thing goes with this one. If I follow the rules that they've presented to me, P to the S is this direction, plus R to the Q. So you'd have to keep in mind that this is going to be added to this. Let's just skip to the R to the Q, and we're going to rearrange it. We're going to add R to the Q later, because you're allowed to do that, as we showed. What's the opposite of minus RS? It's SR. So we're adding SR instead of subtracting RS. So we go there. What's the opposite of PQ? It's QR. Let's skip that. Let's add the RQ now. And now we're subtracting PQ, which is the same as adding QP. And look at that. We end up at point P. So we returned exactly where we started. It's hard to see the way it's written, but if you rewrite them each as what they actually are, let's rewrite them what they actually are. It's PS plus RQ plus SR, that's the opposite of the RS, plus QP. And if you match the letters, see how the last letter here, and you match it with the beginning of each of the next one. So if I rearrange it like this, it's quite obvious. I'm going from P to S, S to R, R to Q, and then Q to P. And since I started at P, I've ended back up at P. I'm exactly where I started from. Sometimes even these visually throw me, because I forget my rules for polygons. Why does the line graph Y, which is X rather, plus Y, plus Z, plus T, equal this red line? I don't quite know why they're asking that. Because we're adding all the vectors together and it ends back up. You could say this, that X is the equivalent as to MR, that Y is the equivalent to RS, and that Z here is the equivalent of ST, and that T is the equivalent of TQ. And since each letter ends with where the next one begins, we are essentially going from M to Q. That's a good explanation. The rectangular box on the right. It always helps if you visualize these things as your room, your bedroom, or something like your bedroom, because it's very hard to visualize on paper. The rectangular box shown is labeled OX. They just call OX. They've relabeled the distance OX, a vector called X. Think of this as the floor of your room. Think of these as the side walls of your room. And think of this last thing on the top as your ceiling of your room. So your ceiling is this block up here. You've got 4 walls. And your floor is this block down here. So they've relabeled distances between the 2 letters as x, y, and z. Express each of the following vectors in terms of x, y, and z. Well, by, so if I look at by, it's here to here. Okay. Well, this is a rectangular box, which means all the corners are right angles. And that means this line here is parallel with this line, and with this line back here, and with this line back here. It also means with a double parallel, this line is parallel with this line and this line, and parallel with this line and this line and this line and this line. And it also finally means that the walls straight up are parallel, and I should have three arrows, are parallel with each other. So it's a lot easier when I can expand this thing. So maybe I'll make a copy and expand it. Yeah, there we go. These are all parallel. And that'll help you understand that if they're parallel and all the angles are 90 degrees, that'll help you understand that this line here is the exact same length as this line, and this line. This line here is the exact same length as this line, and this line, and this line. Now, they've told me it's a rectangular box, which means these end sides are also the same length, because they've told me a rectangular box, which means these ends are squares and the other parts are rectangles. So technically, these are all the same as well. Now, by is the distance from here to here. And I know it's the same over here as x, but x is going this way, and by is going the other way. So it's not the same as x, it's the same as minus x, because it's going the other way. So the answer here is minus x. xb, so this is minus x. xb is going from here to here, which is the exact same as y on the other side. So xb is the same as positive y. OB is diagonally cutting over here, right? And if you remember that x over here is the same as x over here, that means to get from O, which is O to y and y to b, is adding y plus an x. You might say, well, that would end up here, but you got to remember you're adding tail to head. So here's the head here, and when I take the x and put it over here instead to the head of y, like that, it's clear I end up at b. So that means this here is x plus y. Or actually, it doesn't matter what order you put in. X plus y or y plus x. X to y goes from here to here, and you can see it goes backwards on the minus x. So backwards on x is minus x, but then it follows the normal y. So you can write that as y minus x, or you can write that as minus x plus y. It doesn't matter, because the distributive property for vectors is the same. So this is x plus y, and this is minus x plus y. O to Q goes to this corner and ends up in this corner. So that's kind of tough to figure out. But remember that z is up. So you can say, well, I'm going up this z. Then I've got to go along this z to p, which I know is the same as my y, because they're parallel and they're the same. So that means I'm going up z, the same direction as y, and then to cross over here, I'm using the same direction and distance as x. So it's plus x. So this one here is plus x plus y plus z. Q to z is a little bit tricky. Q to Z is going back here, which I know x is that way, so going backwards is minus x. And then R to Z, we already did that one. R to Z is the same as y, which goes that way, but the opposite direction, so it's minus y. So what we do is we get minus x minus y to go from Q, R to Z. So that's minus x minus y. And finally, P to O, we here, if we go this way, we're going the opposite direction of the x, so we're going minus x, and then when we go down to O, we're going the opposite direction of the z, which is going up, so it's minus z. So that means this last one is minus x minus z. And that's using these little vectors that have been relabeled to travel around the square. So essentially, instead of writing these segments over and over again, we get to designate them as simpler letters. It makes our life a little easier. And all of math is about finding ways to make the previous math a little easier than the previous science. Okay, if this is a parallelogram, that means that this is the same as that, and this is parallel with that. It'll also mean, since it's a parallelogram, that this angle here is the same as this angle here, and this angle here is the same as this angle here. It also, I believe, means that their lengths here and here are the same. So x and y represents sides of this parallelogram. Draw vectors that are equivalent to x minus y. Okay, x, so we're just taking x as is, but minus y is going to be the opposite direction. Okay, and if you were to travel it, it would be from C to B, but then at B it's going to go up to here. So the equivalent vector is this. Did I get that right? No, I didn't get it right. So I'm essentially taking x and subtracting y, so I'll do it in the right order. I'm taking x, and I'm going to subtract this y, and I end up with this line. I'm going to draw it in red. If I were to place that on the parallelogram, look at that. It's the same as the diagonal there. So you could also call it dB, because this is going that way. So you could say it's dB. So draw vectors that are equivalent to x minus y. It would be dB. And that's about it. What about y minus x? Okay. That's very similar. We're taking y. We're keeping it the same, like that. And I actually should have made it in black. But now we're subtracting x. Like that. And the resulting line, and you should also put an arrow on all of them. I'm a bit lazy about the drawings. Like that. And I'm just going to actually keep it as a movable line, which means I'm actually talking the same now as this vector, BD, which kind of makes sense. To calculate x minus y, the formula, to calculate the magnitude between this distance, you're essentially finding that distance there. The formula x minus y squared is equal to x squared plus y squared minus 2y cos x, which makes sense. That's just the cos law. You're taking, since this theta exists over there as well, it doesn't matter which one you use, to find this line, the distance between B and D, it says absolute to say it's just the distance, you follow the cos law, which says you're using this side and this side, which is the same as y, and you're using this theta, and you're using it as the square of BD is equal to the square of x plus the square of y minus 2xy cos of this angle. And the angle's always opposite the line you're interested in the cos law. So they're essentially just saying cos law. Show by drawing the vector y minus x that the formula for calculating x minus y is the same. Well, because these are parallelograms, this distance here and this distance here are going to be the exact same. And that's because if you look at the triangles, that triangle is congruent with that one, and this triangle is congruent with that one, but they're also all congruent with each other. That with that, and that one with that one, which means the lines in distance will always be the same. And that can be just shown with congruence. But if you're going to show it with rules of thumb, you could do it. Oh, hang on. Let's see. There we go. Well, x minus y we determine is right here, right? So x and then minus y is this right there. Okay. You're saying show that that's the same as y minus x rather. So y minus x is the opposite direction. Well, it is the same. BD is the same, exact same length we just measured. So if I look at x minus y, it goes like this and then like that. But it's the same line. If I look at y minus x, it's this and then that. It's there. You're essentially going to create congruent triangles no matter what. And if you're talking about the opposite line, so this is theta over here, you can't really use this line until you figure out this mystical thing here, except you can. It'll be 360 minus 2 theta divided by 2. And that'll be, let's call it gamma. That'll be those two angles opposite. That's because this all has to add up to 360. This angle is going to be the same as theta, and these two opposite angles are going to be the same. So you can use that formula in for there. It also turns out that theta plus theta, no, you can't make that argument. In water, Maria can paddle at the rate of 7 kilometers an hour. The current in which she paddles has a speed. What velocity does she travel downstream? Okay. They just want you to represent it in vectors. So, fortunately, this is 2 dimensions. You're either going downstream, so the stream is moving this way, or you're going upstream against the stream. Downstream, the vector is in red, this. So the stream is moving this 4 no matter what. If Maria is moving with the stream, let's say this is Maria's vector here, 7. It all depends which way she's moving. If she's moving with the stream, we add them. Since it's the same direction, we can see that the magnitude from here to here is 4 plus 7, 11. So she moves with the stream, suddenly she's going 11 kilometers an hour. If she's moving against the stream, we have to reverse her direction. So she's not moving in the same direction as the red arrow, she's moving opposite. Which means we would take this arrow and add it to the head of the red arrow. And I'm just not going to quite overlap them. Like that. And the green arrow represents 7 this way. Well, it's clear that they both overlap this 4, and the leftover distance is 3. And it's also clear if she starts here, and the stream takes her to there, and then she's paddling to there, that she ends up here. So it's clear that the vector she has left is from here to there. And it's clear that vector is also 3. So you end up with a long vector here when she's going downstream of 11, and when she's going upstream is 3. And what's interesting is the difference between these speeds, which is 8, is twice the speed of the river. And that's because in this direction we're subtracting the speed of the river once, and in this direction we're adding the speed of the river once, and the distance between -4 and +4 is 8. Counterintuitive. So we've done that, and we've done that, and we've done that. So we did them all accidentally. In the example above, a ship, in the example involving a ship being towed by 2 tugboats, draw F1 and F2 and theta and F1 F2. I missed the example of the ship drawing 2 tugboats. Ah, there we go. There, we got it. There we go. They made us come all the way back here. What meanies. Okay, we'll just keep it like that in case we need it. We'll go back to the question. In the example involving shipping, draw F1, F2 theta, and F1 plus F2. Okay, let's draw F1 plus F2. There's F1. There's F2, which means the resulting direction that the tugboat gets pulled is this green line here. So this is both the distance and the force that the tugboat will be pulled. When these 2 boats are pulling with their equal weight, the tugboat will move in that direction and that speed. And that's where the tugboat will end up, or not the tugboat, but the cargo ship. They're doing. Just a moment. I've just got a call coming in. And so when we draw F1, F2, so there's F1 and F2. Here's F1, F2. And the green line's their resulting thing. Theta. So what's interesting is theta is going to be the result of, in black, if I draw a line here, theta is here, and the resulting angle will be sort of a partial of the theta. But you can figure out by understanding it over here 180 plus theta, and you'll also be able to figure out that theta is also over here, because this line is parallel to that line. This line there is parallel to the forward movement of the tugboat, so theta is also over here. So you can figure things out. Show that F1 plus F2 is equal to the Coase law, essentially. Now I'm surprised F2 here is not squared. It should be. That might just be a mistypo. That might be a typo. But if we're looking at that, we can see that this black line here is the opposite of this line, which is F2, the opposite of this line, which is F1. What's interesting is proving that that is theta. And how can I prove that that's theta? let's see if I can do it with drawing the lines differently. If that is the angle here, and I draw this line here from F1, right, I can also make the same argument that it's down here. Okay. So if I know the angle here is theta, if I draw a line here, it's also theta. And if this was a parallelogram here, theta would also be here in the opposite corner. What's interesting is proving theta is this angle here as well as the tough one. Maybe if I also add F1 over here, I'll see it a bit more clearly. So it's clear that this is theta here. It's clear that these are parallelograms. Yeah, so I believe should actually be 180 minus theta, I think. Yeah, I'm gonna have to leave that because I don't know if I agree with just they forgot the square for sure. But oh, they've changed the formula. Ah, okay. Let us pull up the cos law and see how this one differs. So it's normally minus 2. They've got plus 2. So there's a minus in there. I see. Yeah, okay. Showing that added together is the same as adding 2. I still think that's a mistake. I think that still has to be squared. And they've done it like that. Okay, so I think I've just got to redraw these triangles. So I also know that this is going to be theta. Here, if I draw the tugboat F2 this way, and if I join it that way, this becomes minus F2 because I've essentially put it in the other direction. And they did indeed forget the square. So, and this is still F1. I've just made my theta in this corner by making it a minus F2, which means I have to use minus F2 in the cos law. If I use minus F2, it's not going to matter here, which they did indeed forget to square. It's still going to be minus F12 squared, which is still plus F2 squared. And this is still just F1, so that's not a problem. But right here, when I do minus 2 times F1, which is normal, I have to do a minus F2 here, and then I can use cos theta, which is there. So essentially I'm drawing a triangle over here. I'm using my Z theorem to show that theta is the same over here, and that way I can use theta as my opposite line. This line is the same magnitude as this green line over here. It's just the wrong angle. However, they're asking for the magnitude, which is what this absolute value means. The magnitude of this line will be the same here. Adding F1 to F2 is the same as taking F1 and subtracting F2 in terms of the magnitude. Just the directions changed. So that allows me to use this theta in the Z theorem. If theta is here, theta is also here. And because this tugboat here is definitely pulling along the same direction, they're both parallel, allows me to use the Z theorem. And this line here is the same magnitude as that line here, except that this part here is minus F2. This minus F2 makes a plus 2 here. But everything else about the theorem is the same. You can still, they just forgot the square here. This is definitely squared. It's not plus f2. And that's why. I hope that was clear. In order to create a triangle with theta intact, I have to use a minus f1 vector here. But this line here that I'm interested in is the same magnitude as this line here. It doesn't matter how I add the vectors. That line is always going to be the same as that one over there in terms of magnitude. Not in terms, it's not the same vector. It's pointing in the opposite direction, but the magnitude will be the same. And that allows me to use this. But in so using minus f1, it changes this minus here to a plus. Everything else is the same. They definitely forgot a square here. This is not true. It's got to have a square here. All right, moving on. A small airplane is flying due north at 150 kilometers an hour. Just do that. Due north, 150. When it encounters a wind 80 kilometers from the east, so it's coming from here and going from there. Wherever you want to remember your compass, start with north, draw a thing like that, and the thing to the left is always west. Once you get those two down, the rest are just opposite directions. They're always, it's always 90 degrees to each other. And a compass has 360 degrees. Okay, that means if I go 90 degrees to the west of north, I end up pointing exactly west. Alright, so this plane is moving 150 north when it sees a wind coming from the east. So that means it's going west at 80. And they want me to say what's the resulting ground velocity, which means what is this green line right here. Well, this is a Pythagoras theorem because both winds happen to come from pure directions. And I've just said they're 90 degrees apart. So I can say that this distance here is the same as the square root of 80 squared plus 150 squared. Okay. And if you do it in your calculator, 80 squared plus 150 squared is equal to that, and then you got to square root it. And so the resulting vector is this. It should always be longer than either of the two sides. So it should always be long. If you get a value smaller than 150, you've made a mistake, because the hypotenuse of a triangle is always the longest side. So there you go. So if x is 7, so if that's 7 in magnitude, and y is 24, if the angle between these vectors is 90, determine x plus y and calculate the angle between x and plus y. So they want you to do between x and x plus y. Now be careful, this is x, this is y. So x plus y would be this. So here's x over here. That's x. Here's the resulting line vector they're looking for. And they're asking for the angle between x, which is here, and x plus y, which is here. So they're asking for this angle up here. Well, using Pythagoras theorem, I know that this side length, which is what they want, determine x plus y, is the same as the square root of 7 squared plus 4 squared, which is the same as the square root of 49 plus 16, which is the same as the square root of 65. And we're just going to leave that as an accurate distance. We're not going to square root that yet. But I also know the angle here, following SOHCAHTOA, if I wanted to make my life easier, I can use the TOA part. because the angle here is the same as the opposite line over the adjacent line. And since I have nice exact figures, I can put that into my calculator. It's going to come out as a decimal, and I can then do arc tan, which looks like this on your calculator, tan with a little -1, and it'll spit out the angle like this. So you take 4 divided by 7, so that's the actual tangent. Then you go to your trig functions, and you don't hit tan, you've got to go the reverse direction to find the angle that produced that tan, and you get a nice angle of this. Now it depends what they wanted to round up to, but they didn't say, which means this cute little angle right up here is 29.74 degrees. And since this is 90, this other angle right down here is 60.256 degrees right there, because they all must add up to 180. The resulting distance is 65, and they don't tell us units, so it's just 65. So if they want it in, this is a very accurate, you'll find in math that they just want it in square root. But if you said to X number of decimals, you would take the square root of 65, and here's why you don't take it. Because no matter what part of that number I use, I'm losing accuracy. So if I round up to there, I get that. If I round up to there, I get that. So whatever it is, meters, kilometers, whatever the units they give you, that's the length of this line in red right there. And if they said, okay, they said if this is east, remember it was 60, what was it, 60 point whatever. If this is east and they wanted me to give the compass direction, I could say it one in two ways. I could say, well, you're going east, but you're also going 60.256 degrees north. So that just means east direction, but add this angle in here towards the north. Or I could also write it as I'm going north, but 29.744 degrees. Let's see, would it be to the east or to the west? It would be to the east, which means I'm going up here. And you might say, well, wait, the east is over there. How are you going in 29 degrees towards the east when it's technically the west? It's because that angle right here is also right there. So if this is north, I'm going another 29 degrees to the east. So I'm either going east 60 degrees up from it, or I'm going north 29.4 degrees east of it. That's if they wanted it in compass directions. 13 and 14. I might skip 15, but I get that. So if AC are two unit vectors with magnitude 1 with an angle between, so we might as well draw it. We got AB like that, and we've got AC like that, and they're both the same length. This is A, this is B, and this is C. Calculate A plus B, A to B plus A to C. Oh, and this is at 150. Okay. So they want us to calculate A to B, that, plus A to C, like that. And you might say, how do I figure out the angles? Well, remember that the original A to C is over here. This is A to B, and this part here is A to C, which is also over there. And if you remember your rules, the angle here is 150, which means the angle on this side is 30, which also means the angle over here is 150, because these are parallel, which means this angle here is 30. Calculate, they just want the magnitude. They just want the distance here. But we needed this 30 to use our coast law. So they want this green arrow right here. Calculate A to C. So this is essentially C. So they're essentially saying A to B and A to C, which happens to be the same as, it's not really A to C because A to C is up here. This would be a new angle called D. But anyway, so they essentially just want the green line. Well, we know this is 1 and this is 1. They've given us a magnitude of 1 for both of these lengths, and we know that's 30. So looking at our cos law, the length here, which we'll call x squared is equal to ab squared, which is 1, plus bc squared, which is 1. So we can just say 1 plus 1, minus 2 times ab, which is 1, times abc, which is 1. So it's just minus 2 times the cos. What's the angle opposite x? It's not 150, it's 30. Cos 30. So I have to figure this part out before I can add it. But I can add these. So 1 plus 1 is 2. So I'm getting 2 minus 2 times the cos of 30. But remember, this is equal to x squared, not x. So I got to go 2 minus 2 times the cos of 30 equals, and I get this small distance here. And you're just going to want to make sure, you're going to take your cos of 30. It's 0.86, so it's most of 2. Yeah, minus 2 is equal to that. Yeah. Then you want to take the square root. Because if x squared is equal to that, the square root of both sides will give you x. So x is actually equal to 0.555. Now, right away, I would say to myself, I've made a mistake, because x should be much longer. Should be much longer than that. So I'm going to pull up my cos law. There it is. Nice, 2 times b and c, c squared. Yeah. So I definitely got it right. I think where I've made a mistake here is in drawing it. So it makes it look like I've got an error, but in reality, when I look at the original degrees, right, if I take the original degrees, 150 is much wider than that. So if I've got an A, a C, and a B here, really the B is over here. So by drawing it the way I've drawn it, I've made it look like the angle's not possible. But really, this is a 150 degree angle. It's actually almost all the way further. It's more like this. Like that, and like that. And this angle here is 150. So when I connect them, I'm actually connecting two lines that are like this. So it does make sense, especially since this is supposed to be the same length as the other one. It's more like that. It does make sense that this line is quite short. And it's actually, if you look at 150, which is almost 180, it's actually going to look more like this. So your instincts, the way I drew it, is to say, no, that's not right because this line is huge. But that's because I didn't properly draw the 150 angle before, which means this little angle here is 30, which means that's the little angle here, 30. So now the way it's drawn, if this length is 1 and this length is 1, it makes sense. That's much smaller than 1. If you're used to Pythagoras, you just got to remember a hypotenuse in this case doesn't apply. It's not going to be the longest edge. I just misdrew it. You can see where visual representations can throw you off. Okay, ABCD is a parallelogram. Diagonals BD and AC meet at point E. Okay, let's just draw it. So it goes A to B, B to C. Now there's quite a few things that are, you have to remember the rules of the parallelograms. This side's going to be the same length as this side. This side's going to be the same length as this side. These two angles are going to be the same. These two angles are going to be the same. And they're talking about, since they make it A, B, C, D, they're talking about the diagonals here, A to C, and the diagonals here in blue of B to D, which are actually going to be the exact same. Will they be the same length? I think they'll be the exact same length. And that's because all these triangles are congruent, which means if you add up this length to this length, it's the same as that length to that length. Prove that EA plus EB plus EC plus ED is equal to 0. Oh, okay. That's actually easier. So the point in the middle they've called E. So EA, we're just going to draw them. We're just going to draw them and connect them. EA goes like that, and it's not quite drawn properly, right? And then we're going to add EB to it. And then we're going to add EC to it. And then we're going to add our final ED to it. Quite clear that we've come back to the same spot. And it stands to reason. It wouldn't make sense otherwise. It wouldn't be a parallelogram otherwise. Oh, this might be hard because I forget my midpoint rules. Ooh, yeah, I don't know if I can prove that because I forget my midpoint rules. There's something about the angle has to be 90 at that point, and you can prove congruence. You'd probably have to go look up midpoint angles, midpoint rules, and what exactly is the definition of a midpoint. It might help. So, rules of the midpoint. What is a midpoint in a line? And then just look at your images. Okay, in a rhombus. So then, yeah, there's various things. Midpoint in a square. In a polygon. Yeah, I forget the rules for it. But I believe the rule for this one is that this has to be 90 to 90, or it has to bisect in there. If PM is equal to MQ, so if these are the same and these are the same, prove that 2 times RM is the same as this plus that. No, I'm not going to bother. I mean, I'll come back to it, but I'd have to rehash all these stupid rules. 2 non-zero vectors such that A plus B is equal to A minus B show that A, B must represent the sides of a rectangle. Yikes. I think that'll just be drawing. So we know they're not 0. And we know that when we add them together, it's in terms of magnitude, it's the same result as subtracting them. So let's look at a theory there. If I add 3 and 6, the magnitude is 9. If I take 3 minus 6, the magnitude is 3. So that's not the case. So they must be equal. 3 plus 3, no. Let's see if we can work this out. When does this equal each other? So that's essentially saying when I add it up here, let's say I get 3 here, I would get 3 here, even though this here comes to like minus 3. And they're both non-zeros. Wow. I think only if one of them's negative. Again, theoretical stuff, I don't know if I even care. Ask your teacher about that. And same with this one. These are all theoretical. I'm looking at the practical. Yeah, I could come back, I could go reinvestigate all my rules of midpoints and whatever, but this section is about vectors and adding vectors. It's not about solving these weird polygons that I'll never use in life. And I know you might say, oh, that's cheating. Again, this is about teaching you the practical methods to do all these calculus things. It's not about solving difficult conceptual ones. Just ask your teacher for the difficult conceptual